Okay, so we continue with the third lecture today, lecture number 3. Probably today I think maybe we will finish this chapter 1. I don't know, probably yes. So we were still on chapter 1 about invariant measures. So today we will do more examples and see some techniques to find these invariant measures for certain maps. I like to start with recalling 2 or 3 important things that we have seen. So recall from the last lecture is that one point we have seen was invariance, which this was a definition, mu of E, of course, mu of f minus 1 of E equals mu of E for every measurable set. And also we have seen like the push forward operator, like invariance is equivalent to saying that mu is a fixed point of this operator. And also we have seen a characterization, which is using functions. For every phi mu integrable. So this is one thing we have seen. And remember, we have seen also Poincare recurrence, which is something you derive from invariance. So from invariance, we see that the points, they tend to return infinitely many times to the set where they started, if the set has positive measure. Poincare recurrence, which is that mu finite, so f invariant implies that the number of n such that f n x is in E. This guy is infinite for mu almost every x, where mu of E is positive. Okay. So for instance, this property, you can see many applications of this. If you remember, I gave an example of this contraction map, this map on the disk where everything is converging to the fixed point 0. You can use this theorem to say that that has only one invariant measure. Okay. And also we have seen a generalization of Poincare, which is Gauss theorem. So this is about the first return time. So you have mu in E, where mu of, E in B, a measurable set, mu of E positive. Remember, we have rho E, which is from E to N. So this is the first return time. So if you have that mu f invariant, and so mu f invariant, this will imply that this function is integrable. The integral of rho E d mu equals mu of m minus mu of E0 star. Here E0 star, remember, is a set of points that never return to E. Okay, so today's lecture, we will start with the topological version. These were measurable version of the Poincare recurrence. So we will do topological. Let me see how topological version of Poincare recurrence. So there is a definition of a point, of a recurrent point. So definition. A point X in M is recurrent if there exists nj going to infinity such that fnjx is converging to x as j goes to infinity. If you have a subsequence that approximate this. Now there is now the topological version of Birkhoff of Poincaré recurrence theorem. So theorem is in the book, if you want to check it, is 1.2.4. So let M be topological space with countable bases. Okay, yeah. So this is saying that you have a countable basis for this topology, and we have f from M to M measurable. Mu finite and f invariant. Finite and f invariant measure. So the theorem tells you that then mu almost every point is recurrent. Then mu almost every x in M is recurrent. Okay. It's recurrent. So yeah, here what you need is just, so let's prove this. So we start with, choosing a countable basis, let k in N be countable basis for the topology. Okay. So you want to prove that you have almost every point is recurrent. So first of all, we want to define a set of full measure which consists of the points that are recurrent. So to do that, we suppose that for every k, for k in N, we define uk tilde to be the set of x in uk such that f and x doesn't belong to uk for all n. So these are the set of points they never return to this uk. And by, let's say, by Poincaré recurrence, we have that this set has measure 0, okay? Because UK, we suppose that UK has positive measure because, we can take a basis, a countable basis here where every element has positive measure. So Poincaré recurrence imply that mu of uk tilde is 0.
Why are you thinking that every uk have positive measure?
Sorry?
Why we are taking that every uk?
Yeah, so that's a good question. So that is something you can suppose here, because if there are some uk that has 0 measure, you can disregard that. in this collection. That might not form a basis of the topology, but at the end, because we are going to pick just we going this will be that set will be a basis of of a full measure set, like M of a full measure set. But I'm supposing that I'm saying that if you have some UK here with zero measure, you can disregard that in this collection, and that you will have a basis of a full measure set. It won't be M, it will be another set, but it will still has full measure. So, do you see what I mean?
Yeah, basically, but the answer that why do they have to be, if you require that empty measure, like,
Yeah, because we want to prove this for me almost every x. So we can just, so what you could do is you could, so let's do this. Let's take, okay, so let's do this. Let's create this. Mu of UK positive imply that mu of UK tilde equals 0. You happy with this? Yeah. So yeah. So to be like very precise, this is the Poincare recurrence imply this whole thing. Okay. So you can define now this set M tilde to be M minus the set of UK tilde where mu of UK is positive. This set has full measure. Okay? This set has full measure. Mu of M tilde is 1.
Well, if the measure of UK has positive measure, then the measure of U tilde K it still has 0 measure.
It is 0.
Otherwise, if the measure of UK starts with being 0,
Mm-hmm.
we can just define U tilde as UK, and everything works.
Yes, that's also a possibility, yeah.
Doesn't really change.
Yeah, that's also a possibility. Yes. Yeah. Uh-huh. Yeah, Joan. That's a good point, yeah. You can do this. Okay. So you can see that in any case, so this implies that, so sorry, this is what I wrote before, mu of UK tilde is 0. Because you have two possibilities, whether mu of UK is 0 or it's not 0. If it is 0, this guy will be 0, it is a subset. If it is non-zero, you use Poincare recurrence to conclude this. Mm-hmm. Okay. So yeah, that simplifies. Okay, tilde. Okay, so you have that mu of M tilde is 1. So it is enough to prove that enough to prove that all points in M tilde are recurrent. Okay. So you pick a point, let x in M tilde, and you pick a one in this guy, and you be a neighborhood of x. So you want to find, the aim is to find n, so find n such that fnx is in U. Okay, where U is arbitrary, okay? Okay, now since this guy is a countable basis that exists K naught, and this is an open set, such that X is in UK naught, which is a subset of U, right? By definition of a basis. Is that okay? So this is just the definition of being a basis. So you take any open set, there is one guy here that contains that. And since X is not in UK not tilde, so X in M tilde imply that X is not in UK not tilde. So this implies that you violate this condition. So this implies that there exists some n such that fnx is in UK naught, which is a subset of U. Yeah. So yeah, this is just simple. And an interesting exercise, which is about approximating real numbers, is this. You will do it in the problem session exercise. So f from 0,1 to 0,1 measurable that preserves Lebesgue. Now show that the lim inf when n goes to infinity of n fnx minus x is less than 1. Okay, and yeah, I should mention that there is a Birkhoff recurrence theorem, because if you see the recurrence thing here doesn't use any measure. It's just a topological property. It doesn't, require any measure structure to define it. Now, there is a Birkhoff recurrence theorem. Birkhoff recurrence theorem. It tells you that if you suppose that M is compact metric space, so here now you put structure compact and metric, and also you put some structure on F from M to M continuous. Then there exists a point x naught in M that is recurrent. Yeah. So this is just topological theorem. So I will not do the proof for this. You can look at the proof in the book. It just uses topology. So there's no measure theoretic things like invariance, nothing involved here. So you can check the proof in the book. Because today I want to do some. So, so before we go to examples, I want to introduce some operator which is very useful. An operator which is very useful in finding this invariant measure, which is a Perron-Frobenius operator. So I want to talk about this section. It's not in the book, though. It is used in the book, not explicitly. So I want to do it here. Perron-Frobenius operator. So I will do this for specific system which are the full branch map. So this is something we will study in greater details. Yep.
Where can we find that operator?
The,
In the literature, in some book?
yes, yeah, that's a good book is by there's a book by Lazota Makai. Before I give the title wrong, I will send an email for like a reference for this book for the list of the. So it's something very interesting, which would be also good at the end to do a presentation or something on this operator for a system, because it's very useful to find these invariant measures, to prove ergodicity, to prove mixing. This is a very important operator for this. So I will tell the exact reference by email, okay? Mm-hmm. So let's define. In the book, it is used without stating the definition exactly. So, definition, full branch map. This is something, when you want to study dynamics in the future, this is something very interesting, that even in higher dimension, you can find this structure of full branch map for general systems. So definition. So we have F from. So okay, 0, 1. So it can be any interval, okay? I do it for one dimension. There is also a general version for higher dimensions, but that uses something, that we don't do in this course. So let's suppose that this is a piecewise smooth. So this is piecewise smooth function. So by piecewise smooth, I just mean that there is a countable number of points where you don't have differentiability. Okay. Countable at most countable point where f is not differentiable. So that's what I mean. That's what I mean by piecewise. So f is said to be full branch if there exists I alpha in J. So this is the index set. It can be finite, it can be countable. So J is a countable index set. So there exists, if there exists an index set J, there exists a countable index set J and a partition. So a partition up to, partition up to 0 measure for the, a partition I alpha, for alpha in J. So J is at most countable. It can be finite. Such that we have this F restricted to I alpha, which is from I alpha to I is a diffeomorphism. So to 0, 1, sorry, I think interval is 0, 1 is a diffeomorphism. Yeah. Yes. Sorry. Yeah. So that's why I was a bit hesitant here when I say partition here is up to measure 0 set, because it might not cover the boundaries might not be inside these interval elements. So it's up to measure 0 set, up to Lebesgue measure 0 set, the partition. So you can see some examples. Do you know examples of such? Exactly, yeah. So you can have f of x is 10x mod 1. This is a decimal expansion. So if you look at this map, what it's doing is, you take a subdivision of n intervals, and each of, this should be equal. Each of them maps to linearly to the whole thing after one iterates. So you have n subdivisions. So here, j equals 1, 10, and I equals 1 over I plus 1, 1 over I. Sorry, 1 over I plus 1, 1 over I. Like this. So there's also the Gauss map, which is the continuous fraction. There are many, many examples. And in general, actually, whenever you have a dynamical system on the interval where the derivative is bigger than 1, so if you have in general, so this is a remark that could be good as a presentation or something to include it. So if f is from 0, 1 to 0, 1 is like a piecewise smooth with f prime x is bigger than lambda bigger than 1 for all x in 0, 1. So if you have this, you can always find a power of f that is a full branch map. You can always find a power that gives a full branch map. So.
I think you confused the definition of AI.
Probably. What did I do? You You should start from 0 to...
Yeah, because the I is in the numerator.
Yes. So it's... Oh, yeah. Sorry, I did something. Yeah, yeah.
You didn't use the Gauss Map.
Yeah, yeah, I was, yes. Yeah. So you have I. What did I do? Okay, over 10, yeah. I plus 1 over 10, yes. Thank you. Yeah, yeah, I was having the Gauss Map on my head. So, that exists. So this is a remark that has nothing to do with the course. It's something more technical. There's a power. There is n, such that Fn defines a full branch map. So whenever you have these expanding maps, you can think of full branch maps. So now I want to define now the parent Frobenius operator for this type of maps. Let's see where. Oh, before that, for this type of map, we'll be interested in looking for measures that are absolutely continuous with respect to Lebesgue. Okay, so definition. So let μ1, μ2 be two measures, two finite Borel measures. So we say that μ1 is absolutely continuous. You have probably seen this. I will just recall it. Absolutely continuous with respect to μ2. So this we write μ1 absolutely continuous with respect to μ2 if μ2 of E equals to 0 implies that μ1 of E equals to 0. So remember, from measure theory, there is a Radon-Nikodym theorem that tells you that this is from measure theory. Okay, I'm supposing that we have seen it. So μ1 absolutely continuous with respect to μ2. There exists phi positive that is μ2 integrable such that d μ1 over d μ2 equals phi. So why I said when we study these type of maps, like full branch map or expanding maps, we are interested in something that looks like Lebesgue, because all these full branch map, mostly they have something in common with this type of maps, whether it is countable or not, whether the branch is linear or not. So when the branches are linear, you can see that Lebesgue measure will be invariant. So when the branches are not linear, the measure will not differ much from Lebesgue. It will be kind of equivalent to Lebesgue in this sense. Okay, so the parent Frobenius operator is introduced to find measures that are, absolutely continuous with respect to a reference measure. So to define, let's define parent Frobenius operator. So for that, let M be a reference measure. We take a reference measure. So M is fixed. So, sorry, what I said here is if you're looking for measures that are absolutely continuous with respect to Lebesgue, using Radon-Nikodym theorem, it boils down to finding this density. Because when you find this density, you find your measure. Because you just write your measure, d μ1 equals phi d μ2. Okay? So looking for measures that look like a reference measure in this sense, is just boils down to finding this density. Now the parent-Frobenius operator, sorry, I'm using the vocabulary density. So this is called density in that sense. So a density function with respect to a measure. So phi is density, is a density. Sorry, I'm using this vocabulary without defining it. With respect to m, if you have this, phi is just positive, and the integral of phi dm is 1. Okay, this is what I mean with density. So given, so you write dm is a space of densities. So sorry, I just show phi positive with equals 1. So this is a space of densities. So the definition oh, sorry. Yeah. So given a dynamical system, f from m to m. So remember, I have here I write the measure here as m instead of me because I'm more interested in Lebesgue, and Lebesgue is usually denoted by m. So it's a dynamical system, so at least I'm assuming that it is measurable. And yeah, the parent-Frobenius operator is PF. So it is associated to this dynamical system with this measure, okay? PF, that is defined from dm so it is not defined explicitly. It is defined with this equation, such that the integral of PF phi dm along E equals f minus 1 of E phi dm. So this is the equation that defines this operator. So remark is that if you have a fixed point of this, it defines an invariant measure. So PF phi equals phi imply that d mu equals phi dm is F invariant. Okay. So let's try to find an explicit formulation of this in the case of a full branch map. Proposition so if F is a full branch map, then BF phi at X, this is the sum along pre-images of phi of Y over F prime at Y. Yeah, see, this expression is very interesting and is intuitively telling you that whenever you have an expanding map means that this derivative is bigger than 1. You are hoping to see that you have a contraction here. You see that you're dividing by something less than 1. So intuitively, you see that this operator should define a contraction when you have the derivative bigger than 1, and in which case you can use Banach contraction theorem by choosing a good Banach space there, and you can find a fixed point for this operator, which gives an invariant measure. So having bigger derivative here is something needed to be able to use this operator. Having derivative bigger than 1, like expansion, is important to use. For instance, if you try to do it for a contraction map, it's not any useful because the measure that you find is not absolutely continuous with respect to any other measure, because you will find an atomic measure, a Dirac delta measure. So that measure, you cannot get it from this theorem. So if you don't have like expansion in general, this operator is not useful. Okay, so let's try to prove this. Let me see if I do some examples before the proof or not. No. Okay. Yeah. Okay. So you see that by what you know by calculus, by fundamental theorem of calculus, you have P phi of y of x of x. So by fundamental theorem of calculus, this is d over dx of the x here, yes, the integral from 0 to x of bf phi at x at y dy. This is just fundamental theorem of calculus. Okay, and by definition of this operator here, by what I have, by definition, let me see, okay, I'm okay with time. So the integral from 0 to x of bf phi at y dy, this guy is the integral along f minus 1. So e, the interval is 0x, okay? F minus 1 of 0x of phi of x dx. So this is the definition of this operator here. Okay? Now see that since you are in the case of a full branch map, if this map was diffeomorphism, you don't need to, you know that this is just, again, an interval. This set will be an interval. If f was a diffeomorphism, this set will be an interval, and you can write it, seeing whether you are increasing or decreasing, you can know exactly the bound of the integral. However, f is not a diffeomorphism, but f restricted to some partition element that are given by full branch map is a diffeomorphism. So what you have to do now is to write this as the sum from alpha for alpha in J. So J is what is given by the definition of full branch map of the integral of I alpha intersect with f minus 1 of 0x of phi x dx. Okay? This is nothing because these are disjoint, so you can use this property of the integral. Okay? And at this part here, f minus 1 restricted to, to the preimage, f restricted to I alpha is a diffeomorphism. So here you can just use, so f restricted to I alpha is diffeol. So you can see that this guy is just the integral of I alpha intersect with f minus 1. Sorry, I'm using here something. It should be y because I should not confuse with x. So this you can see that it is just up to a sign because it depends on, I will not write it here. So this is f minus 1 restricted to I k 0, f minus 1 restricted to I alpha, sorry, x of phi x, phi y, dy. So this is just saying whether you have these two, you don't know whether it is increasing or not. So it is plus or minus depending on that. And yeah, and from there you can just see that this guy is just, so this implies that d over dx of the integral, sorry, to x of phi y dy. No, this is yes. Sorry, it should be bf like this. This guy is phi at f minus 1x over, actually I minus 1 at x over absolute value of phi f prime at f minus 1 x. And from there you can just use this sum to have the formula we have up there. So also in higher dimension, remark in general, if f is a local diffeol, you can always have this property. Over the determinant of df at y, where y is in f minus 1x. So, yeah. So just to warm up with this operator, so an easy exercise, just to warm up with this operator to, to get used to this calculation, check that Pf of 1 equals 1, where f of x is kx mod 1. It's 10x mod 1, okay, if you want. Now this is just simple. I mean, it's another way to see that Lebesgue measure is invariant for 10x mod 1. But for Lebesgue measure being invariant for 10x mod 1, you don't need to use this operator, okay? You can just do it by hand, just do calculation. So now let's get to another example, which is the Gauss map. So in section 1.1, we have invariance. In section 1.2, that was Poincare recurrence. So 1.3, examples. So in this, I will just talk about the Gauss map, the circle rotation. And after, I will probably on next week, Monday, I will talk about some flows also, some examples of flows that have invariant measures, like continuous. Where is the Gauss map? Where is it? Yeah. So first example, Gauss map. This is treated in the book. You can also see the proof there. So this is about decimal expansion. Decimal fraction expansion. Fraction expansion of any number in 0, 1. So given x naught in 0, 1, you can define a1. Sorry, let me just do not put 0 here. 1 here. So this is the integer part of x naught. And then you can define x1 to be 1 over x naught minus a1. And similarly, you can define a2 to be 1 over x1. And then you do x2, 1 over x1 minus a2. And then a3 is just. So inductively, what you get is you have this type of expansion, x naught. You write it as 1 over 1 plus 1 over a2 plus 1 over and so on until an plus 1 over and so on. So this is like a fraction expansion. This sequence a1, an give the fraction expansion of this number x naught. Now there is a dynamical system that capture these numbers, that is the Gauss map. So this a1, this sequence an and so on defines the fraction expansion of x naught. Now there is a Gauss map which is G from 0, 1 to 0, 1, that is defined by G of x is 1 over x mod 1. So you can check that this sequence of xi's I define xn plus 1 is just G of xi. So the orbit G of xn, sorry, which is Gn plus 1 of x0. So the orbit of x naught gives some information about the decimal expansion here. And you can see the graph of this in the interval. So see that this map is taking a half here. This is a half. It gets maps to the whole thing, like this. And a quarter gets maps to the whole thing also. 1 over 8. Sorry. It's not linear. And so on. So you would have all these branches like this. So what you have is you have G from a half to 1, from half 1 to 0, 1 is a diffeomorphism. And G also from a quarter to half to 0, 1 is also a diffeomorphism. And you have G from 1 over k plus 1 is a diffeom. See that this map has the property that the derivative is going to blow up. It's going to infinity when you're getting close to 0 because it's 1 over x squared. That's why you see these intervals that are getting smaller and smaller. So what we have here is that we have, if we define ik to be 1 over k plus 1, 1 over k, you have this is a partition up to Lebesgue measure 0, okay? Is a partition of 0, 1 up to Lebesgue, up to 0 Lebesgue measure. Okay? And that f restricted to ik from ik to 0, 1 is a diffeomorphism. Okay? So that, I said F, I'm saying G, okay? Okay. Here G is a full branch map. Branch map. Okay, so you can find a way, you can find the invariant measure for this map using the Perron-Frobenius operator. So one could, if one is you know, well, and you can find, you can do the calculation of the parent-Frobenius operator and find your density, okay? But here I'm going to give you the density, and we just check that this density defines the invariant measure, okay? So for C, positive, so we write this phi x is C over 1 plus x. And define this measure mu of E dx. So the claim is that mu is G invariant. So to prove that it is enough to check that Pg of phi at x equals phi at x. Okay? That this guy is, this C is put here just to normalize it afterward, to make it, the integral to be 1. I think it will be something like log 2 or something at the end, just to have that this measure is a probability measure. You can find what 2 is. What C is, sorry. So let us do the calculation here. So let's write Gk to be G restricted to Ik. Okay, just to do not write this is heavy to carry all. So in this, what is Gk minus 1? This is something you can check. Is 1 over y plus k. This is something you can check. Just solve the equation G of x equals y, Gk. Okay. And we always have G prime of x whenever it is differentiable. So I don't take the points where you don't have differentiability. Is 1 over x squared. Yeah, minus, yeah. Nice. So you have that you can now just Pg of phi at x so this is countable, okay? The number of preimages F minus are countable. Okay. Gk minus 1x over G prime Gk minus 1x. So what is this? This is just, if you do the calculation, this is what you have. I did it once. You should also do it once. So G minus 1. I don't know why I put y here. Sorry. I don't know why. I'm changing. Is this, and phi, the function phi is given by C over, what was that? C over 1 plus x. Yeah. C over 1 plus 1 over x plus k over x plus k squared so this is C over, so if you do this, yeah, x plus k plus 1. Yep. So that you will have y plus k, and then x plus k, sorry, and then x plus k plus 1. Let's see. So x plus k plus 1. Yes. I think I should, do this. And this, you can rewrite it, there's just this trick that you do. 1 over y plus x plus k minus 1 over x plus k plus 1. So this, you can rewrite it like this. And what is this sum? You will see a lot of cancellations, except the first term that is going to stay. So this sum is, you have for k equals 1, so 1 over x plus 1 minus 1 over x plus 2, and you have 1 over x plus 2 minus 1 over x plus 3, and so on. Okay? So you will always see this guy will cancel. So what you would have left is c over x plus 1. So, and yeah, so this tells you that P, G, phi equals phi. This implies that mu, which is phi dm, is G invariant. And yeah, so if you put C equals log 2, yeah, mu is a probability measure. It's a G invariant probability measure. Okay, so let's do another example, which is circle rotation. So this is on the circle, S1. So this is on the circle. And for theta in R, the circle rotation is R theta, which is defined from S1 to S1. That takes Z, maps E 2 pi I theta Z. Like this. Yeah, actually, I kept talking about Lebesgue measure here without saying how it is defined, on the circle here. It's just, if you see that you can define S1 as this modulo by Z, so you have the projection that is defined from R to S1 by just taking any number, you take mod. You take mod 1, though. So this is how the projection is defined. So the Lebesgue measure lambda on S1 is defined by lambda of E equals the measure of the Lebesgue measure P minus 1 of E. You just pick a fundamental domain which is 0, 1. You could have taken, 1, 2, or whatever here. So this is Lebesgue measure on R. M is Lebesgue on R, okay, which is just taking distances, okay, length or distance of 2 points. So this is a countable set. It has a representant in each fundamental domain. So you just pick one fundamental domain and you evaluate the measure there. That's what I mean by Lebesgue measure on S1. So this is just a translation, okay? Circle rotation is just a translation. If you want, you could also see this as, r theta. So another way to see this is you define r theta from 0, 1 to 0, 1, which take x gives x plus alpha plus theta mod 1. Okay? Yeah, if you don't want to, if you want to do it in a closed set without boundaries, so this is a way to do it. But this is the same as this one. So it is a translation, Lebesgue lambda is r theta invariant. So there is now this proposition. R if theta is rational, then every orbit is periodic. And if theta is irrational, then every orbit is dense. Okay, let's do this proof before we close. So if you suppose that theta equals P over Q is rational, then you can see that Q theta of x is x. Okay, this is easy, nothing to say. Now, if theta is not rational, how to prove that every orbit is dense? So theta irrational, at least we can say that every orbit is infinite, because if an orbit is finite, it has to close up. It should be like if an orbit is finite, it should be closed. Okay. It should be periodic. Sorry. If an orbit, I think I'm getting a little tired. If an orbit is finite, it is periodic, and having a periodic orbit would mean that you are rational. So, yeah. So, for theta in R minus Q, then Fn x r theta n x for n greater than 1 is infinite for every x, okay? Every orbit is infinite, okay? Again, if this orbit is finite, that means that you are stopping somewhere. You are periodic. Okay. Now, this orbit being periodic, so being infinite, that means that you can make i.e. so in particular by choosing n m, we can make this guy absolute value of r n theta x minus r m theta x, this arbitrarily small, okay? As small as we want by choosing n and m, okay? Very small. Okay? If you allow yourself to choose n and m, because this is infinite, so you will have an accumulation point, so that means that you can make this as small as you want. Now, to prove that the orbit of x is dense, what you do is you pick an epsilon, pick epsilon positive, and you want to find, want to find so pick an epsilon positive and x prime in S1 or Z prime such that we want to find n such that f n x r theta n, sorry. I'm mixing up everything, zx. Yeah, because I got confused with introducing it differently. Would you forgive me if I do this? So you will forgive me. I just need to skip to be coherent with the notation here. Is in the ball of z prime epsilon. So this is what being dense mean. So any small neighborhood I choose, I can find an iterate that falls in that neighborhood. Okay? Now, so r and theta, this guy I can make it small, so choose n m such that delta, which is this guy, and theta z minus rm theta z, this guy is strictly less than epsilon. Okay, this guy is fixed, is delta. Okay, you choose n and m so that this is just the definition, is less than epsilon. By this I mean absolute value. Notice by the length. So I'm here at S1. So this is R n theta Z, and this is R m theta Z. So I'm abusing a little bit by writing absolute value, but I mean the length of this arc, which is the measure of this arc. Okay. So Lebesgue measure is invariant. So for every, so lambda is r theta invariant for every k delta. This is the same. R. So first of all, this is the same delta R n minus m theta z z. Okay. By invariance, you can apply the pre-images, and for every k, also delta equals R n minus, I don't know even why, okay, n minus m minus k theta z minus R minus k, okay, I do plus here, k theta z. So by invariance, we have all these are delta because it just translates by R, okay? So this guy being smaller than epsilon will enter, so let's suppose that we have here our point z prime here. Epsilon is slightly bigger than delta. So this interval here will intersect this one. So delta smaller than epsilon imply that there exists k, such that this interval here R k theta z is in the ball B z prime epsilon. Okay. Yeah, maybe we stop here for today, and yeah, next week we will finish with this chapter and go to the existence, the chapter 2 about existence of invariant measures. So I stop here for today.
We're going to study the chapter 1, the whole chapter 1.